Okay, good afternoon, everyone. This is the last talk of today. We have Aayusman Mallick with us. He's a B.Math student here at ISA Bangalore, and he'll be talking about hypergraphs. And so over to you, Aayusman. So you can continue your talk from here.
Okay, welcome everyone to the last talk of today on hypergraph theory and hypergraph container. Um, you guys are of category NB, so I hope you guys are within the range of class 8 to 12. So, is my presentation visible to you all?
Yes, it is.
Okay,
Yes.
so let me begin. So, basically, the topic of today is hypergraph theory, and I will take you guys up to introduction of hypergraph containers in an intuitive manner. Okay, so the brief recap would be graphs. Okay, so I don't know how many of you are familiar with the concepts of graph, but here it is. I have mentioned it on 7 for the sake of it. Uh, a basic definition of graph is that it is a set or it is a pair of two sets where first set contains the elements which we colloquially term as vertices, and the second set in that pair is the set of unordered pairs of elements from the first set. Uh, Another way of saying it would be it is a structure consisting of a set of objects where some of the pairs are related, some of the pairs are related in a two-way relationship. Like if there's a set of friends and there's Alice and Bob, and Alice and Bob is friends, then we say that Alice is friends with Bob. Now, whenever we are graphs have many interesting properties, and they are also visually very charming. But what happens when we try to model some relationship which are not two-way but multi-way? Like graphs can be used for like modeling friendships, or let's say any tournament or matches or game schedules where one versus one teams or one versus one players are present. But what about, for example, say relationship between more than two entities from a set of n entities? Like on the current context, we can think of like how the weather of a place is dependent not only on climate but also variable local factors like this. How can we model those things? There are many more examples present. So, for that kind of situations, from graph, we generalize to hypergraphs. Mm. Hypergraphs can be thought of as where we were considering pairs of elements to a forming relationship. Here we consider tuples. Those tuples can be two tuples or pairs, or can be three tuples, or in general we term it as k tuples. Uh, that is, we consider k tuples from the set of vertices as elements of edges. Formal definition of a hypergraph is a pair of V, where V is a set of elements and E consists of subsets of elements of V. Now, from this definition, we can also say that elements of E can be any subset of V, because when we are considering about hypergraphs, we are not considering specific pairwise edges as such. We can consider single vertices, which is trivial and trivially true, and also like three vertices forming a edge, four vertices, and so on. So we can consider that our edge set capital E to be a subset of power set of V without any restrictions. Why the term without any restrictions comes to place? Because the restrictions would have been, this is the case of a general hypergraph. The restrictions would have been like for graphs where the elements of E would only have been pairs. So if we would have not written for the eighth set of graph to be a subset of a set of V, which is true, then we would also have to restrict it by saying that for all small e belonging to capital E, we would have restricted uh, that their cardinality is 2. That is for okay, let me change. Like if we have considered mm, for graphs, then that the set of edges would surely have been a subset of power set of V with an additional restriction of that for all edge belonging to the edge set is 2. That is, all edges are 2 tuples. This would have been our restriction. Now, since the general concept of hypergraph is pretty vague, for our practical purposes or to study specific characteristics, properties, or some generalizations from graphs, we introduce a notion of uniformity, where uniformity denotes that if a hypergraph is A uniform, then each of its edge contains exactly k many vertices of that hypergraph. And from this uniformity, we can surely imply that all the standard graphs, or graphs as we say it, are nothing but two uniform hypergraphs, or graphs are a special subset of hypergraphs. Now, for hypergraph, many a times it is also said that for our sense of intuition or for sense of visualization, when we are not doing set based or probabilistic based computations, that we imagine the edges to be some sort of blobs and all. And yes, that comes handy for vague generalizations, but we can see that hypergraphs can also give rise to some interesting patterns when we try to illustrate them, some interesting diagrams. And I've did one of the examples here. The plane is an example of hypergraph. It is an example of three uniform hypergraph. That is, each of its edges consists of exactly three vertices. Now, plane is nothing but consider a triangle and it's inscribe an encircle within it and draw its altitudes or perpendicular bisectors. Both are equivalent. Now, consider the vertices as the vertices of the triangles, the points where the circle, the perpendicular bisector, and the side of the triangle meets, and the intersection point of all three altitudes or bisectors, which is also a case of here in the diagram, is also the center of the encircle. Then we get 7 vertices, three from vertices of triangle, three from the contact points of incircle and triangle, and one from the center. And we get 7 hyper edges where each of the edge connects exactly 3 vertices. 3 edges are 3 sides of the triangle, which connect 2 vertices of the triangle, and and the middle point of the sides on which the perpendicular bisector falls, or on which the incircle touches. And 3 perpendicular bisectors themselves. The perpendicular bisectors connect the middle point of one side, the opposite vertex of the triangle, and the center inscribed by the circle. And one hyperedge is formed via the incircle, that is the circumference of incircle, which connects the 3 vertices, which are the midpoints of the 3 sides. This is a nice illustration of a hypergraph. Now, we proceed to a related concept regarding graphs and hypergraphs. Like, what do we term as independent sets? Now, why are we trying to consider this? It will come handy. But in case of graphs, independent set is a subset of vertices that contains no edges. That is, when we pick some of the vertices from the set of all vertices, then we find that no two of those vertices share an edge, or no two of them are connected. Intuitively, when we are thinking through the two-way relationships, think of the independent sets as the entities you have chosen, which are from the same system or from the same set, but no two of them interact in any way whatsoever with each other. Now, in case of hypergraph, there's a slight tweak in the definition. That is, for hypergraphs, subset is the independent set is a subset of vertices that do not completely contain any hyperedge. Like, from this diagram of Fano plane, we can consider an independent set of the hypergraph to be this point, one of the vertices of the triangle, and the center, and suppose another of the vertices of the triangle. Now, the when we are in case of these 3 vertices, when we consider either pair of them, we see that they share an edge, but that edge is not completely contained within those 2 vertices, but they also require another vertex which is not present, but independent, because the edge is not completely contained within this set. It can be said this is the way we think of independent sets, because in the multi-way relationships, like as I said, for weather of a localized area, we don't get a complete picture of weather even if we exclude one of the factors playing a role there. So we need all those entities present for them to formulate that weather. Similarly, generalizing that concept, we see that to form either of the edges, like either of the edges are for this edge or for this edge, we would always need either this vertex for this edge or this vertex for this edge. So the, the edge is not completely contained within the set of those vertices. So these are the sets of these are independent sets. This is a particular tweaking or a particular notion to remain careful of for independent sets in hypergraphs. Now, from independent sets in hypergraphs to reach up to the concept of hypergraph container methods, I would use an example and illustration to successfully present the points of hypergraph container lemma. That is, now when we have a graph, we can sort of think many interesting questions or properties, but for a graph G, we have one of the most uh, basic questions or one of the most foremost questions of graph theory, which was solved in the early years of the last century, uh, within 1908 or 1910, before World War One, sometime like that. Like for a graph G, where n vertices are present, this guy Mattel posed this statement, and later it was proved by Mattel or some people else. I don't properly remember that it contains at most n square by 4 edges, or if n square is an odd number, that is it's a number of the form 4k plus 1, then it contains at most the box of n square minus 4 number of edges. Like the question posed was, uh, what would be the number of maximum edges for a graph with n vertices so that it contains no triangle, and this was this was the answer which we concluded. Up to this, do you guys have any questions or queries or any ideas how we can proceed from here? Like, how can we proceed from Mentel's theorem?
Could
Arishan?
you repeat what is a hyperedge?
Yeah, sure, sure. So, for we are defining hyperedge as uh, where we are defining the edges of graphs as pairs, unordered pairs of vertices or unordered pairs of elements from the first set. In case of hypergraph, we generalize that notion to be on any subset of element of V to be the element of the set of edges. Uh, is your query clear, Anurag?
Yeah, yeah. Thank you.
Yeah.
And sir, in this Mandel's theorem, we are taking normal graphs, right? Or the hypergraphs?
No, no, we are treating normal graphs. I mean, graphs. Do you guys have any way of thought like how can we proceed? I mean, at first I should ask, how many of you were familiar, at least knew the term graph or knew the notion of graph? Like I'm seeing Rayansh, Samanyu, and Avinav response. Anyone else, or did you hear the term graph in the context of mathematics? Like beyond the, I think in schools in class 8 to 10, some coordinate geometry. Beyond that, uh, yes, obviously. So if you guys have heard, so then it's fine even if you have not heard. So now I would like you guys to think upon the question. Like, suppose you are given in points, like for the vague generalization, for the sake of intuition, I am considering in points in whatever plane or whatever is, I mean, in basic plane, two-dimensional plane, you consider in points. How can you consider construct a graph such that no triangles are formed within those endpoints, and among the sets of those kind of graphs that you get, the graph you are trying to find has the maximum number of edges? Like, I'm giving you guys 1 or 2 minutes. After that, I will proceed. But can you guys think of anything? It's okay if you don't. Like,
Sir, could you, sir, actually repeat the question once again, because your voice is coming a little slowly, so we're not able to hear much.
oh, sure. I was asking the question that suppose you yeah, you are in a plane, or you are working in a plane, like two-dimensional plane, and you are given n many points. Now you are tasked to create a graph with these n many points such that this graph contains no triangles, and among all the graphs with n many points which contains no triangles, the graph you are trying to create has the maximum number of edges. Abhijit,
Yes,
was I
sir. Yes,
clear?
sir. Yeah, I actually heard ki we are trying to form triangles, so I was a little confused what I do trying to tell.
Oh, okay. And our basic motivation would be, if we can find this kind of graph, then how many edges would be there? Like, how many maximum edges when can we construct? And someone knew, yes, you have written. Yes, and someone knew, how do you define degree of a vertex for the vertex X? Like, suppose from the in many points you choose two vertices, uh, two vertices arbitrarily. Like, after that, how are you proceeding? How are you proceeding for degree of the vertex? So your end goal is to find how many maximum number of edges can be found, found such that they
Uh,
contain no
could we
triangle.
possibly using the formula of n less than equal to 2n minus 4 or something like that? Not sure, but I guess I've read somewhere, so I was asking.
Okay, Abhijit, can you repeat once again? You said
I
something
was
about load of.
yeah, I was asking ki could we be using something like the formula of the edges where e is less than equal to 2n minus 4?
Uh, I don't know if it can be proceeded in that way, but yeah, if you uh, if you can come up with anything more concrete, then okay. And also, I sorry if I don't know your proper name, but in the chat, someone named Curiosity wrote, what you have written is right, that you can we can achieve the floor in square by 4 with bipartite graph, but how are we being sure that this is the
Sir,
maximum number of
just a second.
edges?
Just a second.
Okay.
As you said, we are using n many points, and if we are considering n equals to 10, just for example, I'm not saying
Yeah,
it's
yeah.
just. I guess there we can only draw maximum of 16 edges, and if we are it's in planar 2D plane, and if we are considering non-planar, I guess for 10 we can draw up to, I guess, 25 edges for by the
Uh,
Mentel's theorem.
yes, by the Mantel's theorem, but I am arriving at the point. How are we arriving at Mantel's theorem? Yes, by Mantel's theorem we can work this out. But I'm trying to illustrate what is the motivation behind Mantel's theorem, or how are we arriving at the conclusion of the Mantel's theorem. Also, please don't call me sir. I'm just some years senior of you. You can call me anything else. By my name is also fine. Also, Rian wrote a proof. Yes, yes. Riansh, your proof method is absolutely right. In fact, uh, the proof of Mantel's theorem, as I know, for graphs engineer, I is proceeded in this way in this presentation also.
Do you like?
Also,
Are you trying to like the Mentel's theorem's formula, like what we try to take it through means the n square by
y-
4 edges,
yes.
or
How are we arriving at that bound?
yeah, are you
Or
asking the proof or the conclusion of the proof?
no, the proof, or how are we arriving at that number? Like the main motivation or the main question was maximum number of edges for a graph without any triangle for n many vertices, right? Also, Swayanshu choose a vertex with max neighbors and ensure that it has no edges with its neighbors for triangle free profit. So, Swanshu, I would ask you one thing, like if you are choosing a vertex with maximum neighbors, and are you trying to say that it has no edge with its neighbor, or it shares no no common neighbor with any of its neighbors? Like because if it has no edge with its neighbors, then how are we saying that it is a neighbor? Like for example, let me draw something. Suppose okay, here's what okay. So suppose these are the 3 points, and we draw. Uh, Pardon my drawing skills. I hope they're illustrative as bit and nothing else. Like suppose these are the ages. Suppose. So then how are you considering the neighbors if there is no age present? Like for this vertex, say we label this vertex as 1, 2, 3, 4, 5, 6, 7, and 8. How are we determining the neighbors of 1 if we uh, without any edges, or if we consider here for 8, if 8 has in this graph 8 has no edges or no relationship with the other 7 points, so then how are we determining the neighbor of the point 8? Okay, observe it now. Yes, Anshu, yes. No age in common, or yes. Instead of saying no age in common, you can also say it like for an arbitrary vertex and among its neighbors, if we consider any of the neighbors arbitrarily, then these two vertices should not share a third common neighbor, else they would form a objective vertex some degree with the so yes, of course. Yes, Abhijit, you have given a nice construction. In fact, uh, from your construction, okay, let me check on this. What is in CK? I can do it here. So, um, okay, yes, Abhijit, you have given a
Yes, sir.
another nice argument in another way. I mean, in fact, this is the we construct complete bipartite graph after Mantel's theorem. I mean, visually we can think of complete bipartite graph quite easily, but in mathematically this can be argued as a valid construction technique through which we conclude at complete bipartite graph. Okay, so
Yeah,
let me proceed.
I was trying to ask you that, like you were trying to find the conclusion of the proof, or we are trying to make the constructions and the proof. So
No, no, it's fine, it's fine. Okay, so I have written it in with hurry, so it's all in notations, but uh, let me clear as Rayansh wrote in the text box that if we consider uh, D to be D of V to be the number of neighbors of a vertex V, and then if we consider the edges, uh, consider the pairs from the edge set, then we see that neighbors of uh, d of x plus d of y summed over the set of edges is always less than mn, where m is the number of edges and n is the total number of vertices. Now dx plus dy is always less than n because since we can conclude it uh, from the Shamanyu's argument that where Shamanyu started like we can choose two vertices and so that not sorry not Shamanyu but Swayanshu's argument that we can choose two vertices and two neighboring vertices and we need to make sure that they don't share a common neighbor because if they do then that would form a triangle. We can inscribe it down into the triangular inequality of uh, this dx plus dy is less than equals to n for all xy neighbors, or to be more specific, for all xy pairs belonging to edge set. Now, if there are n many edges, then taking this summation over a edge set would uh, give us that bound to be m into n. And also, when we are considering this summation of neighbors degree of x plus degree of y over this edge set, we can see that the term dx, or we consider the, uh, for the vertex x, we consider or we count all of its edges, and all of its edges also appear dx many times. So dx appears dx many times. From that, we are make, making this equivalence that uh, su- summation of this expression dx plus dy over the edge set is equivalent to saying summation over set of vertices d square v is less than equals to mn. And also, if we take the summation of degrees of all the vertices, then we can see that each of the edges is double counted. For at first, from here we can consider as at first for x, and then for y, then we can make sure we get that summation of degrees of summation over all vertices for degree of vertices is twice the number of edges. And on that we apply Cauchy-Schwarz inequality, and from application of that Cauchy-Schwarz inequality we get that this summation of square of degrees over vertices is always greater than equals to 4m square by n, where n is number of edges and n
Could
is
I
number of
interrupt
vertices.
if you
Yes,
don't
sure, sure,
mind?
sure. Yes, sure.
You have written m is here the number of edges, and you have written m is greater than equal to n square by 4. But the Mendel's theorem tells, doesn't it tell कि m the number of edges is less than equals to n square by 4?
Okay, have I made a mistake here? Okay, so thank you for pointing it out. I think I mistook the inequality sign here.
Second the last
Uh,
inequality.
Yeah,
when
yeah,
I
second line.
typesetted it. Yeah, thank you for pointing it out. I didn't see I wrote it, mistyped it. Okay, so yeah, thanks a lot for pointing it out. And yeah, so from this construction we get that maximum number of edges is at most n square by 4 many times. And after that, from the construction given by Obrodip, we can conclude at this graph. This is a complete bipartite graph. Here I have taken n to be 10. So from Obrodip's construction, we get k to be 5 when we are maximizing the term n minus k into k, and we get a graph of this sort. Complete bipartite graph means when we are given n many vertices. Uh, for bipartite graph, we mean when we are given n many vertices, we partition them into two sets, and no uh, and vertex from one set does not contain any edge within its set, and contains all the all possible edges towards the other set. And complete bipartite graph means where the number of elements in each of these bipartite sets are same. Okay, now we are up to this we were trying to count uh, maximum number of edges in a triangle free graph. But what about when we try to count how many unique triangle free graphs are possible, or like more formally speaking, how many triangle free graphs can be formed with in many vertices up to isomorphism. I mean, isomorphism means both graphs are equivalent. We can uh, transform from one to one. We can find a bijective function from one graph to another such that all the relations of the first graph is maintained in the second graph. So this is our focus, and now we use hypergraphs to count this. So can you guys think of in any way such that uh, we can count the number of triangle free graphs which we can get for in many vertices?
By the oh, a triangle free the asymptotic behavior. There is some
The
formula.
asymptotic behavior.
Yeah, I'm not sure of the formula.
I mean,
I can't still remember correctly, but I guess it's something
I mean,
2 to the power n square by 4 or something. I'm not sure.
I mean, you are proceeding in the right way, but don't think of it as a formula. Like, try to come up on your own. If you didn't know the formula, I mean, suppose you guys don't know anything, any formula or anything, you guys just know up to the basic facts discussed today, up to Mantel's theorem. Now, how can you try to think of number of triangle free graphs? I mean, if you guys know any formula, it's good, but the point of this talk or the topic of discussion is to find out the motivation and rediscover through that path. So why don't you try to think of in any way instead of relying on formula?
By actually trying to make the graphs and finding out the edges and trying to maximum edges and then trying to see what is actually happening with that. I guess so.
Okay, but when we are trying to count it individually, suppose it can be done for smaller values of n, like suppose n5 or n6 or n7 or whatever you consider too small. But after certain many values of n, suppose for n100 or greater, won't the computation become much more complex,
Yeah, yeah,
or
yeah, yeah.
the number of
Yeah, because
steps?
up to we go to n10, it becomes a thousand. So maybe up to 100, it will go in billions and trillions.
So can you think of in any other way? Like, this is a very nice way of thinking. I mean, what you proceeded, it was the earliest possible way of thinking, counting the individual triangles. But can you think through any other way, any construction, anything? Okay, so I am proceeding beyond this. Now, here is where our the hypergraph theory, or what we would conclude today on hypergraph containers, would come to help. Now, for thinking or counting triangle-free graphs on n vertices, we consider the graphs. So at first, I need to make sure one thing I have not written here, that all possible triangle-free graphs on n vertices would always be a subgraph, would always be a induced subgraph of the complete graph K, where complete graph just denotes all possible and choose two edges are being drawn. Like, do you guys disagree with this, or it's okay? Like, all possible graphs which we can consider on n vertices, uh, or to be more precise, all possible set of edges on n vertices is is a subset of all n choose two possible edges. So from that we try to count instead of individual triangle-free graphs. We are trying to find out is equivalent to saying we're trying to find out triangle-free subgraphs of Kn, considering all n vertices and not all of the n choose 2 possible edges. Now, this graph is known as Kn, complete graph on n. So Kn, now we are transforming Kn, or we are trying to construct a new hypergraph from the relations present in Kn on the basis of what we are trying to count, or what we are trying to count, which should not be there as forbidden or as such. Like, we are creating a hypergraph whose vertices are all possible edges of Kn. Then for Kn, the number of edges is n choose 2. So the vertex set of hypergraph is nothing but all the edges of Kn, or the number of vertices of this hypergraph which we are trying to construct is, pardon me, n choose 2. Also, in this hypergraph, we find that for each of the vertex in this hypergraph is nothing but an edge of the Kn, and now the vertex, the degree of an edge in Kn, where we are considering degree on the terms of hypergraph, degree of a subset of vertices is okay. Yes, degree of a subset of vertices for a hypergraph is, think of in this way, that is, degree of a subset A is nothing but the number of edges of the hypergraph such that our given vertices are all present in that hyperedge, or our given vertices are a proper subset of that hyperedge. So from that notion, we can come back here and think of that degree in hypergraph degree. The degree of each vertex of the hypergraph is nothing but the all n minus 2 possible choices for the edges of Kn to form triangle. And why we are considering triangles as edges? Because that's how we are defining that edge set of this hypergraph is nothing but the triangles in Kn. Now, since a
Sir,
triangle has, yeah,
why are we considering triangles exactly? I couldn't understand.
uh, yeah. So we are trying to count the all possible we are trying to count the all possible graphs up to isomorphism on n vertices which do not contain a triangle. So we are trying to construct a hypergraph which would have its vertice, through which we are trying to come up with some technique such that from that hypergraph we can count triangles. Now, why are we considering triangles? That we will come in a bit. So
So what is
yeah,
isomorphism? I couldn't understand. What does it mean by isomorphism? I
okay.
correctly, I don't know the spelling. Like if it is isomorphism, what you said, I couldn't understand.
I mean, it's okay. By isomorphizing, I was trying to say that if you are given two graphs, suppose F and G, and you consider a map from F to G such that all the vertices of F are mapped into the all the vertices of G, that is it's a one to one, and all the relationships between the pairs of vertices, that is the edges, are also similarly present in the all the uh, edges or all the pairs in the graph of G from F to G. I mean, it's a fancy way of saying basically they are equivalent graphs. Uh, we are just considering two different representations or something like two different diagrams, but one can be transformed to another or something. So even if you don't consider that, our main motivation here was counting triangles, counting graphs with invertices with no triangles. And for that, we concluded that counting number of such graphs is equivalent to counting the number of subgraphs of Kn with all its vertices but not all of its edges. Now we are now when we are trying to uh, count those number of subgraphs, we are translating this problem into hypergraphs with the construction that vertices of the hypergraph are nothing but edges of the Kn complete graph of n vertices, and we are considering edges to be triangles in Kn. So here we can get 2 to 3 notions very clear that since triangles has 3 edges, we can surely say that our constructed hypergraph is 3 uniform. And as in the case of as the number of triangles possible in the Kn graph is n choose 3, then our cardinality of edge set for the hypergraph would be n choose 3, and also for degree of each vertex in hypergraph is basically equivalent to saying number of triangles in which given edge of Kn would be present. That would be n minus 2, because two vertices are there in present in the edge, and we can choose any of the n minus 2 edges to form a triangle.
Sir,
Now here, yeah.
what is the, can you explain again the degree of a hypergraph? Like, what do you mean by that? I couldn't follow that part a bit well.
Okay, sure. So degree of a hypergraph, degree of a hypergraph, not degree of a subset of vertices of hypergraph is nothing but counting the number of edges on that hypergraph such that for the set of vertices we are given, those are properly contained within that edge. When we are considering, okay, so let us go back to the plane example. When we are trying to consider the degree of, suppose, say these two vertices, like these two vertices of the triangle, or in the case of this hypergraph, these two vertices of the plane, then the number of edges such that in which both of these vertices and some other vertex or vertices are present in those edges. Like these vertices are properly contained within those edges. In this case, we can found that these two vertices are uh, properly contained within this edge, and no other edge properly contains these two vertices. So coming back to here, so here up to this I think we are clear. Now we are coming how they should help us in considering the triangle free graphs. So I also introduced the notion of independent set in graphs and hypergraphs. So if we follow from that, an independent set in hypergraph consists of set of vertices that does not completely contain any edge of that hypergraph. So when we are thinking of that in terms of the complete graph Kn, it contains edges of the complete graph Kn such that they do not form a triangle. So when we are counting number of independent sets of this hypergraph, we are counting triangle free graphs with n vertices. So both of these countings would be equivalent. Now here we are applying Mantel's theorem that at max a bipartite graph with n square by 4 edges, box of n square by 4 edges has no triangles, and any of its subsets is also triangle free. So for Kn or in so here we are considering in Kn or in the hypergraph, each of the when we consider the bipartite graph instead of Kn, when we consider the bipartite graph with a bipartite graph of Kn, that is Kn minus 2, Kn minus 2, then we get that any of the subset we consider those are triangle free. So when we are counting individual independent sets of the hypergraphs, any independent set of hypergraph, or when we are considering any of the vertices in hypergraph, any of those sets we are finding is triangle free. So when we are counting the vertices of the hypergraph, that is same as number of edges in Mantel's theorem. So as Mantel's theorem contains n square by 4 edges at max, such that it contains no triangles and any of its subset is triangle free, we can say for that hypergraph we find at least 2 to the or we can say that in the hypergraph at least n square by 4 many vertices are present, uh, from which we can consider any of their subsets as that they will always form an independent set. So from that we get that if we take each of the vertex of the hypergraph has two choices, either to be present in the independent set or not. From that we get at least 2 to the power n square by 4 or 2 to the power floor function of n square by 4 triangle free graphs. Now from this method we found that we are here counting individually for the individual edges. From this expression it is also more clear that we are counting individual edge vertices of the hypergraphs, which is equivalent to saying we are counting individual edges from Kn. Now for the hypergraph container method, which is quite a recent quite a recent abstraction. I mean, the method was used before in some of the proofs, but it was not proved. It was not proved, or to be said better, it was not generalized. So for hypergraph container method, we can say that our intuition would be, in the previous example, we counted each of the vertices one by one. From that, we counted each of the independent sets one by one. Our intuition here would be we construct a small family of subsets, subset of the power set, of course. Here, the term small or few or forbidden properties, this would be generalized or rigorized later on, is considered, where a small family of subsets would contain the elements such that for any of the independent set we consider, those are subset of some member of this family of subsets. That is, whenever we consider I to be an independent set, then we can find that for the family of subsets to be C, we can always find an element in C. An element in C is nothing but the subset of the elements. So, uh, such that in that element, the I is content, or such that I is a proper is a subset of some element E belonging to the family of subsets C. Now, the theorem, hypergraph container theorem, does nothing but groups all independent sets, which we are trying to count here, of a well-distributed hypergraph, which we are constructing from other problems uh, into containers, which is a family of subsets, small family of subsets, such that which are the subsets where the total number of containers or the family of subsets is small. Each of the containers contains few forbidden properties. Forbidden property can be termed as the property which we are trying to enumerate, or property without which we are trying to enumerate. Like here we are trying to enumerate the number of graphs which are triangle free. So here our forbidden property is triangle free, or we are trying to count independent sets where we have considered edges to be triangle in our original problem. And the third property is every independent set I, where independent set I is of the vertices of the hypergraph, is subset of at least one container C, where container is where family of containers is a small number of subsets of the number of vertices, or family of containers is a subset of power set with small cardinality. Now, this term small, few, and forbidden properties, all of these are related to each other, and those really make out the details of the generalized hypergraph container lemma, such that whatever I discussed here, it is just written a bit rigorously here, that total number of containers is small. Each containers contain few forbidden properties, and independent set I. In this case, triangle-free graph is a subset of at least one container C. That is some subset, some graph G from this family of graphs. Here, the relation between small and few, which we are, if we compute or we work out the uh, work out the work out the expressions of the theorem, we get that if we wish that our total number of containers be within, okay, so let me explain this notation a bit. I won't take more than 5 minutes, because we surely cannot enter the real this method. It's such illustration where small o n cube of triangle denotes that for any function f n, uh, for any function f n, if it is said small o n cube denotes that limit n tends to infinity fn by n cube is 0, or more generally we can say that if fn is said to be small o of gn, then we can say that limit n tends to infinity fn by gn is 0. And capital O n to the power 3 by 2. Here, similarly, we denote that when we say that Fn is contained in some capital OGN, we say that there exists a fixed real constant C greater than 0 such that f of n is always strictly uh, less than C of Gn. Like here we are considering n to be like integers as such, but it can also be extended to reals and complexes. Those I'm not entering right now. So this is the meaning of the notation. So here it means uh, some n to the power fn such that fn is strictly less than n to the power 3 by 2, c greater than 0, some fixed constant. And here it denotes each of the container contains uh, f in many triangles where fn such that the function fn satisfies fn by n cube 0. And for the much more generalized statement from triangle free graphs to for general free uniform hypergraphs, here we use the notation of degree and also this notation of delta subscript L of hypergraph. That is nothing but maximum degree, maximum possible degree of a set of L vertices for subscript L vertices from that hypergraph, and IH denotes the collection of independent sets of H. The general statement for this container lemma is vague, so I won't take much more time, but I will just keep over to the use of this method, like whose intuition is as follows. Instead of counting independent sets one by one, we try to come up with we try to construct a family of subsets. Family of subsets is nothing but a subset of the power set which is small, whose coordinate is small. By small, what we mean are to be worked out properly, and such that each independent set is contained within some member of those family of subsets. And this container method is used beyond or is used to improve this bound which we get from Mantel's theorem. And not only this is used for graph theory problems and hypergraph problems, it is used in a wide range of fields in mathematics. I have given 3 examples as applications. Like here we have considered Mantel's theorem for fixed graphs, but what about when we are trying to come up with Mantel's theorem for random graphs or Aayusman random graphs from which this started, from which the consideration of this method started. Also, in recent years, there has been used of container method for enumeration of some free sets or enumeration of sets containing no k-term arithmetic progression. Uh, Here, some free sets we are trying to denote as we are trying to find a subset of n, box of n. This denotes the set 1 to 2 to n in natural, such that none of them satisfies the equation x plus y equals z, and similarly. So thank you guys for attending. So references used for these talks are as follows. If you guys search for hypergraph containers on YouTube, you will find a very nice talk on which was presented on International Congress of Mathematicians in 2018. Or also you can also find the method of hypergraph containers paper on archive on which survey paper that talk was based, and also other resources where this method was first come up with. Okay. So, uh, okay, so I'm ending it here. Okay, thank you guys for attending. I'm ending the presentation. Any queries from you guys?
Yes, if there is any query, you can ask the speaker. Otherwise, we would like to thank the speaker once again. So,
Uh,
if you
could we use the inclusion and exclusion principle to find the total triangle free graphs?
Uh, Not inclusion exclusion principle as per, but there was a nice construction technique used by Erdos and two other mathematicians, as mentioned in the second line of my presentation here, where instead of finding triangle free graphs, they were considering general Kane free graphs, but uh, you can kind of think of it as a sort of generalization of Kane of principle of inclusion and exclusion. You
But
so
can
can we also use branching to find it like branch A edge is not chosen, branch B edge is chosen, like that.
I mean, I exactly don't know about branching, but if I'm not wrong, this finding better bounds of triangle-free graphs, the best possible bound yet has been found via using hypergraph container lemmas, but other
That is found.
bounds
But
have also been.
before introducing the topic, you asked to like there were any other methods we could think of. So I was just asking you, can
Yes,
these also be the methods?
I exactly don't know any proof methods which use branching, but for the principle of inclusion exclusion, which you said, not exactly, but in the paper of Erdos, Kleitman, and Rothschild, they use a method similar to that.
Okay, thank you.
Well, okay. Any more
sir,
questions?
sir, could you again go to the proof for that no triangle free graphs, hypergraphs, that part? I had a question related to that slide once.
Which part?
The proof for the triangle free. Yeah, this slide. Yeah. So here
Okay,
we
okay.
jump from triangle free to bipartite conditions, but bipartite graphs do not contain triangles, but they may contain something as pentagons or something. But in general, triangle free graphs, how do you relate to this? Like, it is very unclear to me that how can we jump from triangle free condition to the uh, this one. Yeah, like bipartite graphs can also not contain pentagons and this, but triangle-free graphs can contain pentagons, a structure like that.
Our basic motivation here, or what we were counting here, were just triangle free graphs, not pentagon free graphs or as such. But if you are interested in that, I would suggest you to follow the same paper I suggested the last person
No, no,
of.
no. I meant that let's say we take the bipartite graph that is there, that is a subset of the triangle-free graph, right? Not the exact set. So
Yes. there can be other graphs.
Yeah. Bipartite, like what I can understand by bipartite is you can't have edges between the same partition that is there, right? Uh, so it may contain it must not also contain any odd cycles, the bipartite graphs, as of the lemma of bipartite. Hello, am I audible?
Yes, you are audible.
So it must not contain pentagons, but in the bipartite graphs. But in triangle-free graphs, there is no restriction to pentagons or any five cycle or
No,
seven cycle
no,
that
no,
is there.
no. There's no restrictions to pentagons or any other odd cycles, and that's why the other methods or other improvements from the lower bound provided from Mantel's theorem have arrived, which has culminated up until now, to hypergraph container lemma.
Mantel's theorem, the optimal bound for the lower bound for this triangle-free condition.
The triangle, so optimal bound for triangle-free condition can be found from this condition, like when we consider the total number of containers to be within n to the power big O n to the power 3/2, then we can find the independent numeric independent set I on the basis of that.
But we proved using Cauchy-Schwarz in the proof for the mantle that it is optimal. Like we showed that it is the optimal bound.
The proof for mantle is the extremal condition of maximum number of edges to be present, but when through container theorem or for triangle free, here we are considering the number of possible triangle free graphs.
Like
Okay, I think
differentiate
if
in-
you have further queries, I think you can go on web, or I would highly recommend going through this paper of Edos, Kleitman and Roth